The data that would answer the question directly: seismic recordings of cracking within the dome, precise deformation measurements, tracking whether its shape is changing in ways consistent with accelerating instability, and gas flux readings showing whether escaping volcanic gas is rising sharply, all face real limitations at Shiveluch, a remote volcano on a peninsula defined by difficult terrain and some of the most persistent cloud cover of any actively monitored volcanic system on Earth. That cloud problem is not hypothetical right now. The most recent advisory from the Anchorage Volcanic Ash Advisory Center noted explicitly that part of the ash cloud was obscured by meteorological clouds even as the advisory was being issued, meaning that at the exact moment this eruption was unfolding, satellite instruments could only partially confirm what the plume was actually doing. That is the recurring problem at Shiveluch. The eruptions themselves are being captured. What is happening beneath the ash, inside the dome, in the hours and days between explosions, stays far harder to see. Now to the part of this story that reaches thousands of kilometers beyond Kamchatka, into airspace that has nothing directly to do with Russia at all. Ash from the most recent eruption was tracked moving southeast at close to 150 kilometers an hour, and within hours the leading edge of that plume was already well outside Kamchatka's immediate vicinity, heading toward the stretch of the North Pacific that falls under the responsibility of the Anchorage Volcanic Ash Advisory Center, the agency that monitors ash hazards across the flight corridors connecting East Asia to Alaska and onward across North America. Volcanic ash is one of the most serious hazards in modern aviation, and it is fundamentally different from the wildfire smoke that has affected parts of North America in recent summers. Wildfire smoke is made of soft, fine carbon particles that pose minimal direct risk to aircraft engines at cruising altitude. Volcanic ash is made of shattered rock and volcanic glass, hard, angular, and abrasive, produced the instant magma is torn apart by explosive decompression. Inside a jet engine, those particles melt at operating temperature and resolidify on cooler turbine surfaces, building deposits that choke airflow and can cause catastrophic loss of thrust. Windshields can be sandblasted into opacity and sensors fouled. The clearest demonstration remains the 1982 British Airways flight that lost power in all four engines after flying through ash from Indonesia's Mount Galunggung, gliding for agonizing minutes before the crew restarted the engines and landed safely. It was not an isolated case. In 1989, the KLM 747 suffered the same all-four-engine failure flying through ash from Alaska's Redoubt volcano, close enough to be directly relevant to what Shiveluch's plume is now approaching. The challenge is that a volcanic ash cloud is not always visible enough for a pilot to simply steer around. At night, or mixed into ordinary-looking cloud layers, it can be effectively invisible from the cockpit, and standard aircraft weather radar is not reliably capable of detecting it, because ash does not reflect radar energy the way raindrops do. That gap is exactly why the International Volcanic Ash Advisory System exists, why Tokyo and Anchorage issue continuous position updates, and why airlines reroute around identified ash hazards even when the sky ahead looks clear. Advisories from this latest Shiveluch sequence are already active, with Anchorage tracking the plume's southeastward drift and issuing forecast positions for the hours ahead. For Western Canada, the busy Trans-Pacific corridor through Vancouver, the open question is whether this ash reaches concentrations high enough at cruising altitude to force active rerouting, the way it did during the far larger April 2023 eruption. That earlier event sent ash across the Pacific as far as the west coast of Canada, prompting Transport Canada and Navy Canada to implement flight monitoring procedures, and at least some carriers departing Vancouver adjusted their trans-Pacific routing in response. The effects on Canadian airspace that time were limited, largely because the plume had dispersed enough by the time it reached North America that concentrations stayed below the threshold requiring avoidance. Whether the current sequence produces a similarly contained outcome or something more serious depends on how the eruption evolves from here, and specifically on whether any of these explosions escalates into the kind of major dome failure that drove 2023 to nearly twice today's altitude. To understand why Shiveluch behaves this way at all, it helps to understand where it sits. The Kamchatka Peninsula extends south from Russia's far east, between the Sea of Okhotsk and the Pacific Ocean, positioned directly above a subduction zone where the Pacific Plate is being driven beneath the Okhotsk Plate at a strikingly fast convergence rate. That rapid subduction feeds intense volcanism along the entire length of the peninsula, home to roughly 30 active volcanoes and some of the most frequently erupting systems anywhere on the Pacific Ring of Fire. Shiveluch itself is the northernmost of them, an enormous stratovolcano complex covering an estimated volume of around 1,300 cubic kilometers, among the largest volcanic structures in the region, and one with at least 60 major eruptions documented over the past 10,000 years. What sets it apart even among its Kamchatkan neighbors is the chemistry of its magma. high silica content and an unusually high dissolved water content make Shiveluch's magma resist flow and trap gas rather than release it gradually, the same fundamental property that drives dome-building, gas-charged, explosively unstable volcanism worldwide. Low silica basaltic magmas, the kind that produce the flowing lava familiar from Hawaiian eruptions, let gas bubble out relatively smoothly. High silica, water-rich magmas like Shiveluch's trap that gas under pressure until it finds a violent way out. That structural pattern, growth followed by explosion followed by partial collapse followed by renewed growth, has defined Shiveluch's entire post-1999 eruptive episode, with the April 2023 event standing as the most significant single failure of that cycle in recent decades, reshaping the crater and clearing the way for the dome growth that has continued ever since, including the newer western dome that emerged in December of 2025. Some volcanologists argue that frequent moderate blasts act as a genuine pressure valve, venting gas and steering the system away from catastrophic failure. Others point to evidence that each explosion chips away at the dome's structural integrity, thinning its support and setting up the geometry for a larger failure later. At Shiveluch, the historical record contains examples of both outcomes, which is precisely why this month's sequence cannot be confidently placed into either category right now. It's worth remembering, too, that volcanic ash hazards to aviation in this part of the world are not unique to Shiveluch. The Aleutian Island chain stretching from Alaska toward Kamchatka sits on the same broader subduction system and hosts dozens of active volcanoes of its own, several of which, Cleveland, Pavlov, Boguslav, and others, have forced flight path adjustments across the North Pacific within the past decade alone. Roughly 300 commercial flights cross this stretch of ocean every day on the Great Circle routes, linking Asian hub cities to Anchorage, Vancouver, Los Angeles, and beyond, nearly all passing within range of one active volcanic system or another. The monitoring infrastructure built to manage that risk, geostationary and polar orbiting satellites paired with atmospheric dispersion models, has improved enormously since the 1980s, but it has not eliminated the fundamental problem. When cloud cover obscures a volcano at the exact moment it erupts, which is exactly what has been happening with parts of this month's Shiveluch plume, a real gap remains between what has actually been emitted and what satellites can immediately confirm. It also helps to put the current altitude figures into a longer historical frame, because Shiveluch has crossed the Bering Sea before. In February of 2015, an eruption sent ash to roughly 30,000 feet, and that plume traveled far enough east to cross the Bering Sea and drift directly into Alaskan airspace, forcing exactly the kind of monitoring and advisory response now playing out again with this month sequence. The eruptions currently being reported in the 36,000 to 40,000 foot range are already higher than that 2015 event, which is one of the reasons aviation authorities are treating this July sequence with the level of attention it is getting. Volcanologists use a standard measure called the Volcanic Explosivity Index, a logarithmic scale running from 0 to 8 that ranks the relative size of eruptions based on the volume of material ejected and the height of the eruption column. For comparison, the 1980 eruption of Mount St. Helens in Washington state registered as a VEI 5 event. The 1991 eruption of Mount Pinatubo in the Philippines, powerful enough to inject sulfur dioxide into the stratosphere and measurably cool global temperatures for roughly 2 years afterward, registered as a VEI 6. Shiveluch's largest documented eruptions in the geological record fall in that same 5 to 6 range, meaning this volcano has demonstrated, over its history, the capacity to produce events on the same order of magnitude as some of the most consequential eruptions of the 20th century. The current explosive sequence, based on the column heights being reported through July, sits toward the lower end of that historical range, significant and genuinely hazardous to aviation, but not yet approaching the scale of the largest events Shiveluch has produced in the past. The altitude and eruption column reaches matters enormously for how far its ash ultimately travels, because material injected higher into the atmosphere gets carried farther by upper-level winds before it settles out. Ash that reaches the stratosphere, generally above about 12 to 15 kilometers, can remain aloft for months and circle the entire globe, the way Pinatubo's 1991 plume did, affecting climate and aviation on a planetary scale. The explosions Shiveluch has produced this month are reaching the upper troposphere and, at their peaks, brushing the edge of the lower stratosphere, precisely the altitude band where North Pacific jet stream winds operate and where ash disperses fastest across the ocean. That is also the same altitude band used by the Great Circle routes connecting Tokyo, Seoul, Beijing, Shanghai, and Hong Kong to New York, Los Angeles, Chicago, and Vancouver. Routes that pass directly over or near the Aleutian Islands in the most direct path of any ash cloud moving east from Kamchatka. The Anchorage Volcanic Ash Advisory Center exists specifically because of the frequency and severity of ash events from both Alaskan and Kamchatkan volcanoes threatening this exact stretch of airspace, and its forecasts, built from satellite imagery, dispersion modeling, and pilot reports, are what airlines rely on to decide whether a given route needs to be adjusted. Rerouting is never a free decision. Trans-Pacific routes are optimized for fuel efficiency using the jet stream, and detouring around a plume that intersects part of that optimal path adds flight time, burns extra fuel, and carries real cost, which is exactly why airlines depend on precise ash cloud forecasts, rather than avoiding the entire region out of caution every time Shiveluch produces an explosion. There's also a hazard from this kind of eruption sequence that has nothing to do with aviation at all, and it is worth understanding even though it is not the focus of this particular update. Loose ash and broken volcanic debris accumulating on Shiveluch's steep slopes after weeks of repeated explosions create exactly the raw material needed for a lahar, a fast-moving slurry of volcanic mud and rock debris that can race down river valleys at speeds and with a consistency closer to wet concrete than to a normal flood. Lahars do not require a major explosive eruption to form. They require loose debris on steep terrain and enough water to mobilize it, whether from heavy rainfall, rapid snowmelt, or crater lake failure. They have historically ranked among the deadliest volcanic hazards on Earth precisely because they can travel far beyond the volcano along valley systems, reaching communities with no direct view of the eruption at all. The 1985 eruption of Nevado del Ruiz in Colombia remains the grim benchmark for this kind of hazard, where volcanic activity melted summit ice and sent lahars into populated valleys, killing more than 20,000 people in a single night. That risk at Shiveluch is a local Kamchatka hazard, rather than one that reaches North American airspace, but it is part of the same broader picture. An actively erupting dome-building volcano is never a single contained hazard. It generates several distinct kinds of danger simultaneously on completely different timescales and in completely different places. None of this means a catastrophe is guaranteed or even likely in the coming days. There is no confirmation right now of a major structural failure of either dome comparable to what happened in April 2023. And the current explosions, though reaching serious altitudes in the 36,000 to 40,000 foot range, are consistent with the kind of repeated explosive venting Shiveluch has shown throughout long stretches of its active history, rather than a single collapse-driven mega-eruption. That distinction matters enormously for how seriously aviation authorities need to respond now versus how they would respond if a genuinely larger event occurs. What is certain right now is that Shiveluch has not finished its eruptive episode. Fresh magma is still arriving from depth. 2 lava domes are still evolving inside. The same crater and volcanic ash advisory centers across the North Pacific are actively tracking a plume that is, at this moment, still drifting toward the flight corridors connecting Asia to North America. The situation right now calls for close, sustained attention rather than alarm, but close attention is exactly the correct response to what is unfolding on the other side of the Pacific Ocean at this very hour. Stay subscribed to this channel because the next update on this eruption sequence and on exactly how far this ash cloud travels before it disperses is coming as soon as new satellite data confirms it.